from Campus Auto Treatment Centers.
Your other time, I think he's there. 2 minutes.
Okay, so I'm going to bend the rules a little bit. This is kind of more of a science talk than tech talk, but it's important because we're making the case for these energy resolving detectors on hand worlds. And all week we've been hearing people say, we need to get all the planets. This is a way to get all the planets. So our motivation, of course, is that exo-Earths are really faint. You can have a nice spectrum like this, but if you put Earth at 10 parsecs and run it through the LUVOIR-B baseline instrumentation, you get 36 photons per minute. That's at the aperture, so there's less at the detector, and that's in imaging mode. So in spectroscopic mode, there's even lower signal per resolving element. So finding a detector that can read signals this small is challenging. And LUVOIR-B assumed an integral field spectrograph with an EMCCD, that's an electron multiplying CCD, with this fancy optical pathway, to which can get those signals, but this design does have some drawbacks. The IFS spreads the planet's light onto many more pixels, which increases the noise level. It has complex optics, so you take a 30% loss in throughput. The EMCCD has a delta QE term, which gives you another 25% loss in throughput. And those are the 3 points we address in this study, but there are other technical considerations. EMCCDs have limited lifetime and are not rad hard. And the current state of the art does not meet the LUVOIR baseline assumptions for noise and QE. And this just shows how much the IFS spreads out the light. And given these difficulties with the LUVOIR baseline, we may want to consider some alternative detector technologies to resolve these issues. And in our study, we looked at energy resolving detectors, which, as the name implies, they count individual photons with precisely determined energies. And recall that we're talking order of 1 photon per second, so that's not difficult in terms of rate for most of the technologies. And because we can resolve energies of individual photons, we don't need an IFS. We can just take spectra in imaging mode because it tags all the photons. No IFS means simpler optics and hopefully higher throughput. No IFS means fewer pixels, because again, we're doing it in imaging mode, so there's lower noise. And because an energy resolving detector takes spectra all the time, we visit all of the target stars for spectroscopy rather than a limited follow-up sample, and we get many more spectra. We do keep the characterization phase of the mission. I'll talk about that in a minute, but we do retain a follow-up spectroscopy phase just so we can get those exo-Earth candidates at quadrature and get better statistics on them. But these are the general advantages to an energy resolving detector. And the main question we asked was, what would these advantages do to the scientific productivity of HAB worlds? And we wanted to try to quantify that to better make the case for them. There are a number of different energy resolving detectors out there. The transition edge sensor uses temperature dependent resistance of a superconductor at the phase transition. MKIDs rely on the kinetic inductance of a superconductor. Avalanche photodiodes use the photoelectric effect to act as a solid state photomultiplier, quantitative CMOS, superconducting nanowires. These are all just different methods to resolve the energy of a single photon. And our approach here could apply to any of them. There will be some differences in the detector parameters, but the advantages of an energy resolving detector in general apply to all of them. But to pick one, for our study, we baselined the transition edge sensor array. And this is a comparison of the detector parameters of our baseline TES versus the LUVOIR baseline of an EMCCD with an IFS. And as I said, the current state of the art for EMCCDs is lower than 90% QE, but even using the LUVOIR assumption of 90%, we got significant gains, because as you can see, there are advantages in every category except for read noise, which is 0 for both of them. All the other categories, and especially pixels per spectral bin, the TES performs better. So with this baseline, we wanted to simulate a survey of exo-Earths with the Habitable Worlds Observatory. And we essentially used the LUVOIR baseline again for that. You've probably seen this inverted pyramid several times during this conference. This is the step-by-step process to find, hopefully, life on habitable worlds. And the challenges of using the IFS motivated a two-phase observing strategy in the LUVOIR report. First one is a detection phase in imaging mode, and that centers on steps 2 and 3 in the inverted pyramid: photometry, proper motion, and constraining orbits of planets. And the idea is we observe each star in the target list 6 times in a wide band pass to try to get as much light as we can. Get robust detections of planets, signal noise of 7, and ideally multiple detections of each planet from which we can determine orbits. And once we have orbits, we can identify the best exo-Earth candidates, roughly 1/6 of the target list, for spectroscopic follow-up. And that is the second phase of the mission, the spectroscopic characterization, which focuses on step 4 in the inverted pyramid, the search for water. And in this phase, we revisit each exo-Earth candidate once near quadrature. And again, we do this with our TES study as well. We take a spectrum at 1 micron. For detection, we want to go up to 500 nanometers where the signal's a little better, but for characterization, we take a spectrum in the water band at 1 micron. And the survey is designed to try to get signal to noise of 5 detections of water. And we implemented this observing strategy with several different tools to simulate a complete survey. We took an existing target list of 200 nearby stars. We used the AYO tool to compute an observing program optimized for detecting and characterizing exo-Earths. So this gave us our list of observations. With the same target list, we used the ExoVista code to compute astrophysical scenes of randomized planetary systems, which outputs data structures that contain all the relevant information for those systems. And then taking the list of observations and the randomly generated systems, feeding them through a coronagraphic and instrument simulation, will eventually give us detection and spectroscopic yields for exo-Earths and other planet types. because with both instruments, we will get some ancillary planets that are in the same scene, but with the TES, we get a lot more of them. Briefly, for the coronagraphic model, we used Chris Stark's 2019 paper, deformable mirror vortex chronograph, and you can see the contrast curve and throughput as a function of separation here. We did use an off-axis telescope model as a mutually averaged coronagraph, so not working on the speckle pattern, just as a mutual average, because we don't know what angle the planets will be at in practice anyway. We used a sharp outer working angle of 60 lambda over d. For the inner working angle, we just relied on the contrast curve there because it cuts off pretty well at 1 to 2 lambda over d. And for this coronagraph model, we generated a list of observations with the altruistic yield optimizer tool. And this is a tool that helps to prioritize targets based on astrophysical assumptions, mainly stellar type, stellar luminosity, distance, and random exozodi term. So there's some random noise in the detectability, and that's why there's some spread in the colors in this plot here. But essentially, the red dots are highest priority because those are the ones for which an exo-Earth are most detectable. And with this optimized yield, AYO creates an observing plan to meet that expected yield. And we use AYO together with ExoVista because ExoVista allows us to apply this observing plan to higher fidelity models of planetary systems and thus further improve yield estimates. And this project is the first in a line of projects we're working on to integrate these tools together and get them to talk to each other to build a more robust framework. ExoVista, I gave a tutorial about it on Tuesday, and it is code that lets you make pretty pictures like this. This is a movie of randomly generated planetary systems with disks with a PSF applied. And you can see the kinds of data structures ExoVista generates, which are very useful for simulating a direct imaging survey. ExoVista is a code that Chris and I have developed, which produces an astrophysical sandbox or universe of systems. It has flexible output, so it does more than just direct imaging. It does RVs and transits. It has an n-body integrator, and we designed it to be efficient on cluster scale, so it's fast and has relatively small file sizes. And put all this together, and this was the result. So we've got number of detected planets from the survey on the left, number of planets with spectra on the right. Solid boxes are the EMCCD, and dash boxes are the energy resolving detector, in this case TES. And you can see we get a few more detected planets. That's because the TES has higher throughput, which allows us to use shorter observing times, which allows us to use a larger target list. But you get many more planets with spectra because we're visiting all of the stars with spectroscopy, not just the follow-up sample. And if you look at the actual number of spectra, it's even higher. There's approximately 8 times as many planets with spectra and up to 7 spectroscopic visits per star instead of 0 or 1. And the exo-Earth yield itself is about 30% greater. So this is the conclusion we reached. You get hundreds of additional spectra for free for basically everything from Earth size up. And you get a larger target list and bonus 30% more exo-Earths as part of the deal. And at that, I'll take questions.
Yeah, do any of these detectors exist in a fashion that will be usable pretty soon?
They, I believe are TRL 3 to 5, depending on the particular detector.
And big enough format? Even?
I mean, the X-ray community
They-
has swung multiple
Yeah.
PS detectors. It depends on the size of the array.
What is the trade-off on spectral resolution? Because I think they don't have as much as a grading can give you.
We
And-
assumed,
Also, sorry, the two questions. The second one is what is the implementation constraint? Because the complexity might be higher to implement the test array, it has to be cryogenic and so on. So
yes, most or I think all of the energy resolving detectors are cryogenic. And we assumed R of 140 for both. So for the purpose of this study, we assume there's no trade-off in terms of resolution.
And, you know, I just wanted one comment. I think one of the most interesting parts of this detector wasn't even in your talk, which is the time resolution. They read out at microseconds. And we got a talk from Olivier Guillaume recently on PSF calibration for ground telescopes. It was interesting, he's using MK detectors, which have very high speeds, whereas EMCCDs and super CCDs have very slow readouts on the order of a minute. So we're still trying to figure out our calibration schemes. But, you know, on top of all these other advantages, potentially, this time resolution, which I think we should include as we think about this.
A lot of band rejection.
Yeah, I mean, these seem wonderful, the obvious question is, well, these are so great, why did you use them during the Livermore study? So obviously the first issue was because they are cryogenic, they have to be cold. Now getting down from like a couple of Kelvin to sub-Kelvin where these detectors need to be, that part's actually okay. The part that scared us was the cryo cooler, jiggly cryo cooler that you would need to go from, you know, warm to like a few tens of Kelvin. So that's why we didn't really even consider them during the Livermore study. However, we realized that if we're going to have servicing for this telescope, we don't have to have a cryo cooler. We can go back and do this, you know, old school Spitzer style and just try it or just shake it. Or coolers.
Very low vibration.
Or low, or.
Sort of. There's high frequency coolers. So there are some, it's something that needs to be studied.
Yeah, it's nice to say maybe the situation with the jiggly, with the cryo coolers, or how do we get from, you know, down to where the adiabatic behind station refrigerators kick in, is maybe not as hopeless as we thought, you know, 6 years ago.
But maybe I can just point out too, I mean, I agree with all these concerns about using it in a high contrast regime. Maybe they're applicable to the general astrophysics instrument as well, or, you know, these detectors might be usable in the general astrophysics instrument, and we talk about it in the context of exoplanet detection.
Sure.
Yes.
Benzine's using MKIDs on, you know, UV optical, so.
Yeah, I mean, from what I've heard,
UV would
basically,
be 90 some odd percent
Yeah.
in the UV, which I'm pretty, there's a middle level of resolution that you can cross this first.
yeah, it kind of sounds like for like the NUV optical, the UV optical near infrared is the only part of the electromagnetic spectrum where someone's using one of these, like they're using one of the far infrared with the MKIDs and the TES and the X-ray. And it's just kind of us in between that are not using them.
Well, one of the issues with the red beam essentially. Yes.
It's the IR background.
What is that one? And if you can eliminate the slime issue with making sure that you're not growing a huge layer of ice on top of it.
That the X-ray folks have sort of demonstrated.
X-ray folks are a little bit more robust to the layer because they penetrate more with it. But, you know,
But the IR background is a legitimate, like, you have photons. The X-ray community uses a thin metal filter.
Any final questions for Alex? Okay, Vanessa, would you mind getting that?
Yeah.
Let's give Alex another round.